So here's somebody who's going to be pushing a chair. And if the net force experienced by an object is positive, that is, if it's a non-zero net force, and imagine they're pushing 120 newtons and friction is resisting minus 90, then we should expect the object to accelerate. The net force here is 30 newtons. Now imagine a car. If an object like a car accelerates, then it increases its velocity. This car, you can see, is going faster and faster. And since Ke is half mv squared, more velocity means more kinetic energy. So if we put it all together, we can say the total net work done on an object will be seen as change in kinetic energy, or net work is delta Ke. Now imagine a boat. The wind is blowing it forward with a force of 2,800 newtons. My wind comes from a fan. But it's dragging a fishing net behind it that offers a resistance force of minus 800 newtons. Let's hook that up. Now the boat also has a frictional drag with the water and the air, and that's minus 1,200 newtons and is working against its motion. If all these forces act over a distance of 50 meters, what's the net work done on the boat? Well, let's make a table. We'll put some rows in for the different component forces acting on the boat. The source of the force, the amount of the force, the distance it acts over, and the work. So the wind, the fish net, and the air and water have different forces, but they all act over 50 meters. And work is force times distance, so we can calculate those. Now, you can use work as force times distance to fill in the individual components of the work, and then you could add them up and find the net work. Since the net work is delta Ke, now you know the sailboat has increased its kinetic energy by that many joules. The net work is the increase in Ke. Now, since you know the delta Ke, you can find the velocity by using the v equals square root 2 Ke over m. If the mass is 800 kilograms, use this velocity equation and actually find the boat's final velocity.